Hey there! I'm the Flash. Just like I draw my power from the Speed Force, with electricity surging through me, something similar can happen right in your kitchen. My buddy Jack asked me to show you how even a lemon can turn into a powerful battery. Let's check it out.
Up lemons. We're not making lemonade, but something just as exciting. We are going to need a fork, so let's grab it while we are in the kitchen. We'll need a few tools: wires, a zinc plate, and a digital clock. Think of this setup as creating our own mini Speed Force. Insert the zinc and then a fork into the lemon. Here's where physics kicks in. The lemon juice, rich in citric acid, interacts with the zinc. Zinc, being more reactive, starts to lose electrons, which are the tiny carriers of energy. This loss of electrons by zinc transfers potential energy to the electrical system we're building. Alright, now that we've got our lemon battery set up with the zinc and the fork, let's connect the clock and see the magic happen. This is where Ohm's law comes into play in our circuit. Remember, Ohm's law tells us that the current flowing through a circuit is directly proportional to the voltage across it and inversely proportional to the resistance of the circuit. Our lemon battery creates about 1 volt of electric potential. That's our voltage, pushing the electrons through the circuit. The resistance, well, that's the part of our experiment provided by the zinc, the fork, and the lemon juice itself. Watch what happens when I remove the zinc plate. With the zinc gone, our circuit is broken, and there's no more complete path for the electrons to travel. The current stops flowing, and the clock turns off. This demonstrates Ohm's law in action. Without a complete circuit, meaning without minimal resistance and a continuous path, the current cannot flow effectively, and our device won't work. But there's more to this story. It's not just about the path that the electrons take, but also the force that drives them. Let's dive deeper into the invisible force at play here: the electric field. Inside our lemon battery, when the zinc loses electrons, it doesn't just create a pathway for electricity, it also sets up an electric field. This field is like a map that directs the electrons where to go, from the positive zinc across the lemon's acidic juice to the negative copper, the fork. Zinc, being more reactive than copper in the acidic conditions of the lemon juice, tends to lose electrons, becoming positively charged. This loss of electrons, known as oxidation, creates a surplus of positive charge at the zinc electrode. This surplus of positive charge at the zinc and the corresponding buildup of negative charge at the copper, where electrons accumulate, creates what we call a potential difference, or voltage. This voltage is the driving force behind the electric field in our battery. The electric field then exerts a force on the free electrons in the circuit, propelling them from the zinc to the copper through the connecting wire. This force can be quantified by the formula E equals F divided by Q, where E represents the electric field strength created by this voltage. F is the force exerted on the electrons by the electric field, and Q is the charge of the electrons.